Derating is the process of reducing the allowable ampacity of a conductor due to certain conditions, such as high ambient temperatures or multiple conductors in a conduit. Derating is often unpracticed in the field. This is likely due to several factors. Firstly, lack of awareness. Some electricians may not be aware of the National Electrical Code or NEC requirements for derating, or may not understand the potential consequences of not derating. Secondly, time constraints. Derating can add time to the installation process, which may be a concern for contractors on a tight schedule. Thirdly, difficulty. Calculating derating factors can be complex, especially when multiple factors are involved. Fourthly, inspector oversights. Inspectors may sometimes miss violations related to derating, which can reinforce the perception that derating is not necessary. The consequences of not derating can be significant. Overloaded conductors can overheat, damaging insulation and potentially causing fires. Overloaded circuits are more likely to trip or blow fuses, interrupting power to essential equipment. Failure to derate conductors is a violation of the NEC, which can lead to failed inspections and potential legal consequences. It is important to always follow the NEC requirements for derating conductors. This includes considering factors such as conduit size. Conductors in a conduit must be derated for the number and size of conductors in the raceway. Ambient temperature. Conductors must be derated for the expected ambient temperature where they will be installed, and more than 3 current-carrying conductors. Conductors in a raceway with more than 3 current-carrying conductors must be derated. By properly derating conductors, electricians can ensure the safety and reliability of electrical installations. To elaborate on the NEC requirements, let's consider specific sections and tables that are pertinent to derating. The NEC provides detailed guidelines for ampacity derating based on various conditions. Table 310.15 B2 A. Formerly Table 310.16 is a foundational table used to determine the allowable ampacities of insulated conductors rated up to 600 volts, typically based on an ambient temperature of 30 degrees Celsius or 86 degrees Fahrenheit. However, when the ambient temperature exceeds this value, or when the number of current-carrying conductors in a raceway or cable exceeds 3, derating factors must be applied. To understand the practical application of derating, let's consider a scenario involving 4 current-carrying conductors in a conduit, each carrying a load. According to Table 310.15 B3 A. If there are 4 to 6 current-carrying conductors, the ampacity must be derated to 80% of its value as found in Table 310.15 B2. This means that if a 12 American wire gauge or AUG copper conductor is rated for 30 amps under normal conditions, its ampacity must be reduced to 24 amps, which is 30 amps multiplied by 0.8. If the ambient temperature is also a factor, for instance, if the conductors are installed in an area where the ambient temperature reaches 40 degrees Celsius, an additional derating factor from Table 310.15 B2 must be applied. For a conductor with a temperature rating of 75 degrees Celsius, the derating factor is 0.88. Therefore, the allowable ampacity becomes 24 amps multiplied by 0.88, which is approximately 21.1 amps. This is significantly lower than the initial ampacity, underscoring the importance of considering all relevant factors. The NEC also addresses specific situations such as underground installations. Table 310.15 B2 B provides adjustment factors for ambient temperature for conductors installed in underground ducts or conduits. These factors are essential for ensuring that underground conductors do not exceed their temperature ratings, which can lead to premature failure of the insulation and potential safety hazard. Moreover, the NEC provides guidelines for situations where conductors with different insulation types are used. Each insulation type has a maximum operating temperature, and the lowest temperature rating of any conductor in the raceway determines the maximum allowable temperature for derating purposes. For example, if a raceway contains conductors with both 75 degrees Celsius and 90 degrees Celsius insulation, the 75 degrees Celsius rating must be used for derating calculations. In industrial settings, where large conductors are common, the NEC provides specific rules for derating conductors larger than 2000 American wire gauge, or AUG. These conductors often have different ampacity ratings and require careful consideration of the installation conditions to ensure compliance and safety. It's also crucial to consider the termination temperature ratings of the equipment to which the conductors are connected. The NEC requires that conductors be sized based on the lowest temperature rating of any connected termination, conductor, or device. This ensures that the entire system operates within safe temperature limits, preventing overheating and potential failures. Furthermore, the NEC addresses the derating of neutral conductors in certain situations. When the neutral conductor carries a significant portion of the load, such as in systems with nonlinear loads like fluorescent lighting or electronic equipment, it must be considered a current carrying conductor for derating purposes. This prevents overloading the neutral conductor, which can lead to voltage imbalances and equipment malfunction. Understanding the NEC requirements for derating also involves being aware of the exceptions and special conditions that may apply. For example, certain types of conductors, such as those used in control circuits or signaling systems, may be exempt from certain derating requirements. However, it's essential to consult the specific NEC sections and tables to determine the applicability of these exceptions. Inspectors play a critical role in ensuring compliance with derating requirements. They verify that conductors are properly sized and derated based on the installation conditions and the NEC guidelines. However, as mentioned earlier, inspector oversights can occur, highlighting the importance of electricians and contractors taking responsibility for understanding and applying derating principles correctly. In addition to the NEC, other standards and guidelines may provide further information on derating practices. These may include industry standards from organizations such as the Institute of Electrical and Electronics Engineers, or IEE, and manufacturer recommendations for specific products and equipment. Staying informed about these resources can enhance one's understanding of derating and improve the overall quality of electrical installations. Furthermore, proper documentation of derating calculations is essential for compliance and future reference. Electricians and contractors should maintain records of all derating factors applied in an installation, including the number of current carrying conductors, ambient temperature, and any other relevant factors. This documentation can be valuable during inspections, maintenance, and troubleshooting activities. In summary, derating is a critical aspect of electrical installations that must be understood and applied correctly to ensure safety, reliability, and code compliance. By following the NEC requirements, considering all relevant factors, and staying informed about industry best practices, electricians can minimize the risk of overheating, circuit failure, and other potential hazards associated with overloaded conductors. Let's delve a bit deeper into the practical aspects of calculating derating, providing some specific examples to illustrate the process. Imagine you're running 6 current carrying conductors of 12 AWG copper wire, THHN insulation, through a conduit in an area where the ambient temperature is consistently around 45 degrees Celsius. First, you need to find the base ampacity of the 12 AWG copper wire with THHN insulation. According to table 310.15, B2, a THHN conductor is rated at 90 degrees Celsius. The ampacity is typically 30 amps. However, we need to consider the temperature limitation of the terminations. If the terminations are only rated for 75 degrees Celsius, we must use the 75 degrees Celsius column, which might reduce the base ampacity to 25 amps. Next, we'll address the number of current carrying conductors. Table 310.15, B3. I provide adjustment factors for the number of current carrying conductors in a raceway or cable. For 4 to 6 conductors, the derating factor is 80%, or 0.8. So, we multiply the base ampacity by 0.8. 25 amps multiplied by 0.8 equals 20 amps. Now, let's factor in the ambient temperature. Since our ambient temperature is 45 degrees Celsius, and table 310.15 B2 is based on 30 degrees Celsius, we need to apply a temperature correction factor. For THHN conductors with a 90 degrees Celsius rating, the correction factor is approximately 0.91 for an ambient temperature of 45 degrees Celsius. Multiply the ampacity we calculated earlier by this temperature correction factor. 20 amps multiplied by 0.91 equals 18.2 amps. Therefore, after derating for both the number of conductors and the ambient temperature, the allowable ampacity for each 12 AWG conductor is reduced to 18.2 amps. This means that the circuit breaker or fuse protecting these conductors should not exceed 18.2 amps to ensure safe operation. Now, let's consider another example. Suppose you are installing 9 current-carrying conductors of 10 AWG copper wire with THHN insulation in a conduit that's running through a hot industrial environment where the ambient temperature can reach 50 degrees Celsius. First, find the base ampacity of the 10 AWG copper wire with THHN insulation. According to table 310.15 B2, THHN conductors rated at 90 degrees Celsius, the ampacity is typically 40 amps. Again, considering a 75 degrees Celsius termination limitation, the base ampacity is reduced to 30 amps. Next, we'll apply the derating factor for the number of current carrying conductors. According to table 310.15 B3, for 7 to 9 conductors, the derating factor is 70% or 0.7. So, we multiply the base ampacity by 0.7. 30 amps multiplied by 0.7 equals 21 amps. Now, factor in the ambient temperature. Since the ambient temperature is 50 degrees Celsius, we need to use the temperature correction factors in table 310.15 B2. For THHN conductors with a 90 degrees Celsius rating, the correction factor is approximately 0.82 for an ambient temperature of 50 degrees Celsius. Multiply the ampacity we calculated earlier by this temperature correction factor. 21 amps multiplied by 0.82 equals 17.22 amps. Therefore, after derating for both the number of conductors and the ambient temperature, the allowable ampacity for each 10 AWG conductor is reduced to approximately 17.22 amps. Again, the circuit breaker or fuse protecting these conductors should not exceed this value. These examples illustrate the importance of carefully considering all factors that can affect conductor ampacity and applying the appropriate derating factors. Failure to do so can result in overloaded conductors, overheating, and potential fire hazards. It's also worth noting that these calculations are based on the NEC and may vary depending on local codes and regulations. Always consult the latest edition of the NEC and any applicable local codes to ensure compliance. Additionally, specific equipment and devices may have their own derating requirements, which should be taken into account when designing and installing electrical systems. For example, some electronic ballasts for fluorescent lighting may require additional derating when installed in enclosed fixtures or high-temperature environments. Understanding these specific requirements is essential for ensuring the safe and reliable operation of electrical equipment. In summary, derating is a critical aspect of electrical installations that requires careful attention to detail and a thorough understanding of the NEC and other relevant standards. By following the guidelines and applying the appropriate derating factors, electricians can ensure that electrical systems are safe, reliable, and compliant with all applicable codes and regulations.